Hi, in this video, we want to take a look at stationary time series. All right, so when we say stationary, there's going to be two types. There's going to be strict and weak stationary time series. Strict is going to be too rigid, too strict of a mathematical criteria to really be useful with real data. Weak stationary time series, we're going to have our expected value will be independent of time, and our autocovariance will depend on the gap between the points of interest and not on the values themselves. Those are the two aspects of weak stationary. All right, so let's go ahead and dig into this. We're going to take some code from time series analysis and applications. Here's the GitHub website where I got the code, and they've got a package in R available for us, and here's some documentation to help us out. Now, the textbook can be downloaded through UCF's library for free by UCF students. All right, so if you need to get everything from GitHub for the package, here is the code that you need. And here I'm just setting up my workspace, making sure that I have the number of digits I want printed out, and I don't have any artifacts floating around in my workspace. All right, so let's go ahead and take a look at strict stationary time series. All right, so this is very strict, as the name says, and to the point where it really isn't even useful for us in terms of mathematical modeling, things that we observe in real life. But we're going to start here, and then we'll go on to weak stationary and then dig in some deeper. All right, so here, if I take the probability function on the different observation points that we're interested in, we're going to have the same probabilities if I shift all of those points. So here, let's say I had, time spots 1, 2, and 3, and some cutoffs, and I wanted to know the probability that the first observation is less than the first cutoff, second observation is less than the second cutoff, and the third is less than the third cutoff. If I was to instead go with fifth, sixth, and seventh with the same cutoffs, I will get the same probabilities. So the punchline of this mathematical statement, and I know it's long, I know it's wide, is that if I look at particular points in time and I shift the time that I'm interested in with the same cutoffs, I get the same probabilities. All right. So it is critical that we are having the same shift here every single time for strict stationary. All right. Well, in general, it's not possible for us to handle, this many variables in a probability statement operationally. It's unwieldy. So let's take a look at with k equals 1. And so here, what this would be if I just have one observation time slot that I want to dig into, strict stationary would say that the probability of our observation being less than or equal to a cutoff value is going to be constant, regardless of which point in time I'm looking at my data. All right, something that falls out from this is that we will have a constant expected value when it exists. So whenever the expected value exists, then we're going to end up having it being the same for every single point in time. Now, something to be mindful of is that a random walk is not strictly stationary because the mean changes with time. All right, now with k equals 2, what we would have going on is that I would have two points of time that I'm interested in with two different cutoffs, or potentially different, two cutoffs. And if I shift the time by the same amount on both of those points in time, then I'm going to get the same probability. All right, and it'll work out that if I take the autocovariance of the time series before and after the shift, I'll get the same autocovariance. And so what's important here to realize is that the autocovariance depends on the difference between the time slots, not on the actual values of the time series. So like that random walk, if my expected value relates to where I previously would observed. And so that means that the expected value is always changing. Now, a weakly stationary time series has two features. First one is that the mean is constant and does not depend on time. Next one is that autocovariance depends on the difference between time, not on the actual values of the observations. It doesn't matter when I'm interested in the time slots. It just matters on what the difference is. So if I have a window, I'm interested in two slots. If I shift over by the same amount, I get the same autocovariance. All right, so what this does for us is that when we have stationary time series, weakly stationary, this gives us some regularity in a time series so that we can estimate what we want very easily. All right, so strictly stationary time series are also going to be weakly stationary as long as we have finite variance. But the converse is not true. Weak stationary time series are not necessarily strictly stationary. I expect for them to not be, in fact. All right, so here's a proposition. If I have a Gaussian weak stationary time series, then it's automatically going to also be strictly stationary. Now, another proposition, if a time series is weakly stationary, then the expected value is going to be a constant. I mean, that comes in the definition. And the autocovariance depends on the shift, not on the time itself. All right, so what we can do to give us a little bit less notation, a little bit less work on the writing, to make things a little bit simpler and cleaner, if I want the autocovariance between 2 points in time, that's equivalent to just looking at the value of the difference between them and 0 for the time slots for the autocovariance. All right. So the autocovariance function of a stationary time series can be written in the standard way. I'm just taking the covariance. So here I'm plugging in that constant mean. And we can also apply the same, apply what we've got so far to autocorrelation. So what I do, I take autocorrelation function, which is the covariance between the 2 points of time, divided by the square root of the covariance on the same point of time twice than the other one. Now, I'll apply that formula that we just came up with, where it's equivalent to just looking at the difference. And all right, so here, this simplifies down in the notation to gamma of little h. Now here, these are the same points in time. This has a difference of 0. And so this is gamma of 0. This has a difference of 0 also. So it's gamma of 0. I got two of them, squaring and then square roots. So boom, we have a slightly simpler formula for us. And once again, this is a type of correlation. Therefore, the Cauchy-Schwarz shows us that the autocorrelation will be between -1 and 1. Okay, so let's look at another example. Let's look at stationary white noise. All right, so I'm talking about white noise. So I have a random normal distribution. And so in this situation, the covariance between any 2 points in time is either going to be 0, they're completely unrelated, or it's going to be the variance of the time when my 2 points in time are the same. And so we have 0 if my points in time are different, and I have the variance of the Gaussian process if the 2 points are the same. And then, of course, correspondingly, looking at the autocorrelation, it's going to be 0 or 1. All right, so white noise satisfies the conditions of weak stationary. If the white noise variant is also normally distributed or Gaussian, it is also strictly stationary. And this can be seen by noting that the noise is IID. So let's go ahead and just take a look. So here I'm just doing a random number generation. So I'm setting the seed so I can reproduce what I've got. Here I'm setting up the white noise random process. So this is just random numbers that have no relationship to each other whatsoever. And when I look at the auto covariance function, then I can just see that it's all floating around 0. Now there is some fluctuation in the data, so it's not exactly 0, but we can see that it's so close we might as well call it 0 across the board. And here is the second type of plotting in the ASTSA package. The ASTSA package is the package that goes along with the textbook. And here it includes partial auto correlation function. And we see it, it's all 0. All right, so now let's take a look at the stationarity of a moving average. So we looked at this example in a previous video where what we're going to do, we're going to take the average of 3 consecutive points where the original time series is a Gaussian normal random variable, IID. And so here we can see that very obviously that the expected value is going to be 0 across the board. And if I go through and do my covariance, what's going to end up happening is that the only time so when I do my covariance, I've got 3 terms, and I'm going to end up multiplying the covariance from all possible pairs when I crunch this out for the auto covariance. And so it'll work out that there's going to be 9 individual 9 add-ins in the summation. Well, whenever I have a different subscript, different time for the observations, the covariance will be equal to 0, so it's going to cancel out. So when I have WT sub 1 along with WT sub 1, WT along with WT, and this should be a plus 1, WT plus 1 with WT plus 1, we're going to end up having a non-zero term when we're doing our covariance. All right, and if we work this out, we can see that this is our auto covariance. And we notice that when h is equal to 0, we're going to get the variance, and this is going to be the largest auto covariance that we get. And as we shift away, the values will get smaller. And here is the correlation. All right, and so let's take a look at an example of this. And so here we can see that the covariance, the correlation actually, just absolutely drops off as we move to the right. Once it gets larger than 2, boom, it's gone. And here we're seeing the same thing, just presented with a different plot. All right, now for this next example, let's see that a random walk is not stationary. All right, well, if you recall from a previous video, the auto covariance of a random walk, and this random walk was based off of the Gaussian. We're going to have our auto covariance is going to be equal to the variance of the original process times the minimum of the 2 times that are used in evaluating the covariance. So remember, in this type of time series, I have a sequence of random variables, And the actual time series I have is the cumulative sum of those random variables. And so it's going to work out if I take 2 points in time, the time that is lesser of the two, all those values are in the sum of both of them. And because of that, we're going to end up getting this to be our autocovariance. Well, we can see that it depends on time. Since it depends on time and not on the split, not on the difference, the lag between the time, we see that we do not have stationary. Also, to further this point, if I have a random walk with a drift, it's not stationary either because I have the coefficient times the drifting time as the expected value. So we can see that a random walk with drift is also not stationary for two reasons. And so we can run an example just to look at this. All right, so now let's take a look at trend stationarity. All right, if it's a trend stationary, then what's happening is that there's a trend going on, and around the trend itself, we're going to have the stationary process. So the expected value is going to go along with that trend, and the autocovariance is going to be independent of time. It's only going to depend on the gap between the points that we are interested in. And so here's an example. Let's say that x of t is our random variable of a constant plus constant times t plus a stationary distribution. So here you can look at this in terms of time. This is a straight line equation from college algebra, like mx plus b. And then I have a stationary time series being tacked on. All right, so when I take the expected value, I can see that I've got a constant, and then I have the trend itself. And so this is trend stationary. Now, when we go through and compute the autocovariance, I'm going to compute the covariance just like I would normally, find the expected value, and I'm going to drop the appropriate values into there. When I do that, a lot of terms are going to cancel out. And so when I drop in x at time t plus h, you notice I have t plus h. Well, you'll notice that the betas cancel out, the alphas cancel out, and I'm going to end up being left with y sub t plus h and mu sub t plus h. Then things will cancel out similarly over here. And I'm left with the autocovariance of y, which we said was stationary. Therefore, boom, we have a stationary about a trend. All right, so let's run through an example. So what this is some data for the price of chicken. And here we can see that there's a trend going on and that there is a process going around it, about it, that's staying along this trend. And here is me just getting a little bit deeper into it, showing a slightly different way, using a linear model. All right, so some properties of autocovariance. So the autocovariance function of a stationary process has several special properties. One, it's non-negative definite. It's bounded by the variance. So its absolute value is less than or equal to the variance at all times. And we have symmetry about the origin. So if I do a negative shift for covariance, I get the same as if I do a positive shift. All right, so autocovariance is non-negative definite. So gamma of H is non-negative definite, ensuring that the variances of linear combinations of the variates will never be negative. All right, so if I do the calculations, we'll get the formulas that will very naturally come out. And autocovariance is bounded by the variance. So my autocovariance in absolute value is less than or equal to the variance itself, and Cauchy-Schwarz can be used to verify that. And autocovariance is symmetric about the origin. All right, so if I take gamma of t plus h minus t, so that's my covariance here, the covariance expected value can be reversed and it doesn't change the value. So I can take this, change the order, and now I realize that I have got t minus t plus h. Doing some simple simplification, boom, we see that it's symmetric about the origin. All right, now, next definition is on jointly stationary. Two-time series, x and y are said to be jointly stationary if they are each stationary and their cross-covariance function is a function only on the lag. All right, so x and y have to be stationary themselves and their cross-covariance only depends on lag, the difference between the times. And when we have that, to be consistent with what we've done so far, I'm going to say gamma of xy of h. And so taking this idea and putting it into correlation, we get the same idea of cross-correlation function. And once again, it'll be between -1 and 1. Now, in general, it doesn't have to work out that the covariance between two-time series for different points in time. Something that's important with this, notice that this is x sub 2, this is x sub 1, this is y sub 1, this is y sub 2, that in general, if I switch the time slots for the covariance, I don't have to get the same thing back. But when I have stationary, joint stationary time series, I can switch it up and it's okay. So it only depends on the lag, not on the time value. And in general, we can't expect correlation to be symmetric. We can when we have cross stationary. All right, so let's look at an example of two-time series that are jointly stationary. So what we're going to do, once again, we're going to take white noise process, and we're going to say that x is the sum of consecutive white noise, while y is the difference between consecutive white noise. And we're going to say that the white noise are independent, and we'll say that they have expected value 0, variance of constant. And then all of these properties are going to hold if we sit down and work through all of this. And so first and foremost, gamma sub x of 0 is going to be 2 times the variance of one white noise process. This shouldn't be surprising. And then gamma for x of 1 is going to be same as if I plug in -1, which is just going to be the variance of the process. We get similar for y, but so we have a negative value because of the subtraction. And then if I sat down and I did the actual calculations for the covariance, this should be a negative sign there. That should be negative. If I sit down and do the covariance, when I expand out with the covariance formula in my so I'll notice that here this term doesn't have any t plus 1, so it's going to cancel out. This t, when it goes with the covariance of this one, will have a non-zero term, and it will be this term will give us a 0 when I go for this to get the covariance in the expansion. So there's only one non-zero term, and that will ultimately give us sigma squared. And if we just, tinker with this just a little bit, I can get the correlation pretty easily. And here is some code just to demonstrate what's going on. So when I have the 2 terms for the variance, that 2 is where I'm getting the 1/2, where the denominator is equal to 2 instead of 1 on this one. And so here is just proof of concept that the autocovariance function is going to give us what we think on x. Here it is on y. Remember, because of the subtraction, I got a negative value over here. And then when I do the cross covariance function, we can see that we have the spike in the middle, and then it rapidly drops off to 0 once they shift away from each other so that the subscripts no longer match. All right, now we can use cross correlation to do predictions. So let's say that I have 2 time series. I know a relationship between them. If I know one value, I can predict the other one. That's the idea of what we want to do here. And so here is just a possible model of y is the time series of a constant times another time series plus a random term. And so we'll say that x sub t leads y sub t if L is greater than 0, and x sub t lags behind y sub t if L is less than 0. And of course, if I need to know, future values of x to predict y, it wouldn't be useful for making predictions. Now, if we assume that our noise term is uncorrelated with x sub t, the cross covariance function can be computed very easily. That I just take the covariance, standard formula, replace y with this, realize that this is just independent of everything else that's going on, and then off of the standard covariance formula, we get that it's the constant times the covariance of x of h minus L. And of course, we're going to get our largest covariance when h is equal to L, and that comes from the Cauchy-Schwarz inequality. So here's just an example just to show what's going on. Yeah, so, oops, I went too far. So here in this situation, x is leading y. Here, y is leading x. Right, now, weak stationary forms the basis of much of time series analysis. The fundamental properties of the mean and autocovariance functions are satisfied by many models that we're going to use when we have actual data to work with. Now, the 3-point moving average example that we saw a moment ago is an example of weakly stationary linear process. But now, what is a linear process? A linear process is a linear combination of white noise. All right, so the reason why we're interested in this is that with white noise, it works out that, Gaussian, we understand Gaussian as statisticians very, very well. And we're going to use this as kind of like a foundation of other types of models to work with. Now, when I have my linear process, we're going to say that my time series is equal to a constant value plus the white noise times a coefficient. And you'll notice that the coefficient, this is j, and t sub j are in the subscripts. Now, something that we're going to do to make sure that other math works out is that we're going to go ahead and say that the coefficients are absolutely convergent as a series. And something that's a little bit different from the standard calculus curriculum is that you'll notice that this series is going in both directions instead of just from 0 to infinity. It goes from negative infinity to positive infinity. All right, and so with absolute convergence up here, this property makes it possible for us to compute, we're guaranteed to be able to compute the autocovariance. Now, when I do this, when I do the autocovariance, what's going to end up happening is I'm going to get zeros whenever the noise terms do not have the same subscript. When they have the same subscript, then the covariance is not equal to 0. And that's where I'm going to get the sigma squared term from. And so here, this gives us what our autocovariance will be. All right, so now in that moving average example, we had all of our coefficients were equal to 1/3, and for -1, 0, and 1, and past that they were all equal to 0. So now let's take a look at the Gaussian process. So a process x sub t is said to be a Gaussian process if the n-dimensional vectors for every collection of distinct points for all possible integers n have a multivariate normal distribution. All right, and so very naturally, we're going to get our mean vector off of this. And we'll get our n by n covariance matrix, which this textbook denotes as capital gamma, which we will assume to be positive definite. And so this gives us our distribution, our multivariate normal distribution. If you've done the theory of linear regression, this should feel very similar to you. If you watch my other videos on linear models, everything is pretty much the same, except I use a sigma for instead of a gamma, but it's going to be the same idea. All right, now some important aspects of Gaussian processes and linear processes is that a Gaussian time series is, if it is weakly stationary, then automatically the mean is constant. The autocovariance function only depends on the difference in time, the lag. The expected value and the variance are independent of time, and all finite distributions of the time series depend only on the lag and not on the actual times themselves. And hence the series will be strictly stationary. Now, if we go into another aspect of theory that I haven't talked about yet, but it's still correct, if we take Wold decomposition, this will give us that a stationary non-deterministic time series with this finite sum is actually a causal linear process. Now, a linear process needs not be Gaussian, but if a time series is Gaussian, then it is a causal linear process with W sub t being IID normal. And so we're going to use stationary Gaussian processes as the basis for many of our time series models. Now, here's an example of a marginal distribution not being enough for us to actually have the property that we want. All right, so if I have marginal distribution of Gaussian, that does not mean that the entire process is Gaussian. All right, so when I say Gaussian, that's for the entire process itself. When I say marginal, that's when I'm considering just one dimension at a time. It's possible for me to consider one dimension at a time, but the whole kit and caboodle is not multivariate normal. And here's a counterexample to that. Let's say that x and y are independent normal random variables, and we're going to let y equal z if x times z is positive and negative z if x times z is negative. Then the situation X and Y are both marginally normal, but the combination of the two is not bivariate normal. All right, well, that's all I've got for you. Take care and goodbye.